Welcome to Unit 2, Modeling with Functions. In this video, we're going to be talking about what's modeling. So obviously the big point of this unit is how to model with functions, and there's several different ways to do that. But in this video, we're going to be focusing on modeling with data. So first thing is, got data. So where do we get data? Data comes from really anywhere. Individuals, places, things, animals, years. I mean, we could look at any object and collect data from it. So what is data then? Well, data is information that we collect from those individuals, places, things, animals, years. So if you think about a person, you could get all kinds of data from that person, right? So we could, what kind of information can we collect from a person? Well, we can collect categorical data. So we could ask that person, hey, what's your favorite flavor of ice cream? And that's categorical because we're going to get words. If you like chocolate, you're simply going to go into the chocolate category because you are a chocolate lover. If you love vanilla ice cream, you're going to go into the vanilla category and so forth. Eye color, that's another piece of data we could collect. You're going to go into the blue category, the green category, the brown eye category, what have you. So you get the idea. The other thing we could collect is quantitative data, and this is measurable numbers. So your height, your weight, how many calories of food you consume per day. So those are things where the information coming back to me is a number that is measurable. It has a unit. And it's also the other key thing is you can make an average of it, right? You could take you can get, hey, what's the average number of calories a student eats in a day? What's the average height of a student in high school and so forth? So it's got to make sense to average the numbers. There's a couple weird examples of categorical data that is a number. I'll give you the most famous one is zip code. So your zip code is a number, but again, there's no units on zip code, and it doesn't make sense to get an average zip code. Like, why would you say, all right, the average zip code is, it just doesn't even make sense. Zip code is really just a category as to where your mail goes to. So it just puts you into a category of where the post office is that is going to get you to your mail. So again, pretty simple information, categorical or quantitative. So how much data or information can we collect from each individual? Really as much as you want. I mean, you could think of an object and you could collect as much information as you want. Maybe you get a bunch of categorical data, a bunch of quantitative data. I mean, it really is endless, but that's what we got with data. Now, what about making connections? Because oftentimes what we want to do is we want to see, does one variable have a relationship with another variable? Like, does your eye color have any relationship with your favorite flavor of ice cream? Or does your favorite flavor of ice cream have any relationship with your height? I mean, it would seem kind of weird, but you could try to look for connections between anything. So we call this type of data investigation bivariate data. Bi meaning two. We're looking at the relationship between two variables measured from a group or an individual. But this is important. If those two variables are both quantitative, we can create a scatter plot of that data to explore relationship. So we can look at relationships between eye color and favorite flavor of ice cream, both categorical. There really might be a relationship there. There could be a relationship between your political party affiliation and where you live. Again, both categorical. But if we want to make a scatter plot to try to put a number to that relationship, both variables have to be quantitative. For example, we could look at height and weight, and we could definitely make a scatter plot of that. So just to kind of demo this real quick here for you guys. We could create a scatter plot with an X and a Y axis, and maybe on the X axis we have height, and maybe on the Y axis we have weight. And again, you can't make a scatter plot if they're not both quantitative. So maybe we're going to have a dot right here, and this dot is for John. And this dot has an X value that will tell us John's height, and this dot has a Y value that will tell us John's weight. So every dot represents a single person, but every dot has two variables for it. Again, the X and the Y. That's why it's called bivariate data investigation, right? And if we have a bunch of dots for John and Sally and Steve and Kyle and Becky and Mary and Jules and David and Russ, then we could really kind of start to look at a relationship between these two variables. All right, so let's make sure we understand what the variables are. So the input values, or the X variable, is considered the independent variable. This is also known as the explanatory variable. So this is always on the X-axis. So obviously X variables go on the X-axis, input values go on the x-axis, and this is known as the explanatory variable. And the y variable, or the output values, is considered the dependent variable because it depends on the x variable. And this is also known as the response variable. This always goes on the y-axis. And the idea is that the explanatory variable explains the response variable, or the response variable is responding to the explanatory variable. So x is the independent and y is the dependent variable. Now, what's modeling, right? So once we have noticed a specific relationship in the data, we could then model that relationship with a mathematical function. So that's why the first step is to having that scatter plot, and that scatter plot with quantitative data, right? Both the explanatory and the response absolutely have to be quantitative, again, number-based. Then we could say, hey, I kind of see a relationship. I kind of see a pattern with all of the dots in that scatter plot. And modeling is essentially trying to find a function that fits that pattern. But we have learned so many functions. So when you see a pattern in a scatter plot, you better recognize what function it is. So let's do a quick review of all the different functions we've learned. First, linear. Maybe we see a linear relationship like this one, where you clearly see the scatter plot or the dots forming a line. The example here is the time on your phone and the number of text messages sent. And the relationship makes sense. If you spend more time on your phone, you're probably sending more text messages possibly. So again, a linear relationship is ax plus b. Now I know that you're usually using mx plus b, but the coefficients are a and b, a being the slope, b being the y-intercept. We could also have a quadratic relationship. So here's two quadratic graphs that we see, a parabola, right? And the model for a quadratic relationship is ax squared plus bx plus c. We've obviously seen that formula before. And we see a pattern where the scatter plots kind of decrease, and then after a little bit of time or what have you, they start to increase. We see that kind of curve, that kind of parabola, right? And you might not see a full parabola. So in this example here on the left, we see kind of a half parabola. But again, it follows a quadratic relationship. We also have a cubic relationship. This is ax cubed plus bx squared plus cx plus d, which I kind of call a snake. We kind of see it slowly curving up, and then maybe it slows down and then continues to curve back up. Or you might even see like these kind of two humps, like a hump and then a valley. But those are cubic relationships. It's important to say that the left side is going down and the right side is going up. So we talk about end behavior there, but that's a cubic relationship. We even have a quartic relationship, which is a fourth degree polynomial, ax to the fourth plus bx to the third plus cx squared plus dx plus e. Pretty long formula there, but that's the model for a quartic. And again, a quartic, both ends are going up, and then in the middle, who knows what's happening, right? Like it could be curving like it is in this example, but we see our data kind of making that weird pattern. That's a quartic relationship. And again, that's honestly not going to be very common in most data, but you never know. It could happen. It is a model. It is a function, right? Then we have what's known as a power function. So this kind of confuses kids a little bit when they first learn about it, but a power function is where we have a power, right? So to be honest, x squared is a power function, x cubed is a power function, even x to the fourth is a power function. But if it gets anything after that, like x to the fifth, x to the sixth, x to the seventh, we just kind of call them power functions. But it's also important to understand that power functions include fractional exponents as well. So even a square root function, which can be written as x to the 1/2, again, because there is a power on the x, it's considered a power function. So a power function is really any function that has a power on the x. And don't just think about integers, 2, 3, 4, 5, 6, but really you could have fractional exponents as well. So x to the 3/4 power, or could even be decimals, x to the 1.24 power. But the point is that there is a power on the x, okay? Now, the other, the tricky thing here is that for functions that have a power greater than 3, it really kind of gets a little bit tricky because even power functions all could look the same. So for example, you could have a function that looks like this, and most kids are going to say, oh, that's a quadratic, but this also could be x to the 6th. As long as both ends are going the same direction, both up or both down, that's an even power, right? So all even powers could kind of look the same, and same with all odd powers. Odd powers kind of go like this. It's that snake. So the idea is that power functions is just kind of a very generic term that represents any function that has a power on it, and including decimals and fractions as well. So keep that in mind. All right, so next up is exponential. So we see kind of this slow curve up or down. So we could have what we call exponential growth, which is what we see on the left-hand side here. We see that the curve is growing. And then we also have exponential decay, where the curve is slowly going down. So increase versus decrease. Now, keep in mind, exponential is when x is in the exponent. So don't get this confused with power functions. Power functions, there's a power, right? But the x is still the base. With an exponential function, the actual variable x is in the exponent. So those are fairly familiar with most kids. All right, then we have logarithmic functions, and this is a function whose model is a plus b times the natural log of x. And again, a and b are going to be coefficients, but that's just kind of the generic form of this model. And this is a model that has a vertical asymptote on the left-hand side, and then it has a slow curve coming up after that. So we typically have, again, a vertical asymptote over here, vertical asymptote over here, and we see the curve is making a kind of real fast increase, and then it kind of really dramatically slows down. And we see that same thing over here. So those are two kind of examples of logarithmic patterns that we see. And the final one we have here is kind of a new one called a logistic. And a logistic is kind of like an S, right? Well, there's actually two horizontal asymptotes, one down here at the bottom and one here on the top. And those are kind of interesting curves as well. They usually do kind of stand out because you'll see that clear S as you see in these two kind of patterns. But that's where we kind of see like a, it starts off as a slow increase, and then in the middle it's a pretty steep increase, and then again at the end it's another slow increase. We kind of see this slow, fast, slow increase over time here. And logistic functions are kind of weird, but they are a coefficient on top, we'll call it C, divided by 1 plus a times e to the negative bx. So the coefficients are c, a, and b. And remember, e is not a coefficient. E is a number, right? It's just an irrational number. So definitely one of the weirder looking functions, but they're actually pretty easy to recognize. But the actual model itself, the function itself, is a little bit weird looking. But we'll slowly get used to working with them. So, what is a model? Let's go back to making sure you understand this. So a model is a function that closely follows the trend that we see in the data. Understand that no model's perfect. We're never going to match the model perfectly, right? In the real world, data just isn't always perfect. But our function should go through the data nicely. It's not going to be perfect, but it should go through the data nicely. So the main purpose of a model is to take an actual x value, explanatory variable, and give a predicted y value with response variable. So once we kind of have looked at our data, and we have picked the model that best suits it, the function that best suits it, and then we find that model, then we can actually utilize the model, right? And I'm going to show you some examples of this in a second. But the big thing here is that we use models to make predictions, because the data that we see, the actual scatter plot that we see, the little dots, that's stuff that we measured and that we saw, but there's always blanks, right? There's always spots in between dots. So if we want to make predictions about data that we didn't necessarily collect, that's where the model kind of comes in handy. And if it's still a little bit confusing to you, as we do a couple examples here in a moment, I think it'll make a lot more sense. Now, we could also use models to work backwards. So here we can use a model to help us solve for an x value with a given y value. So models kind of work both ways. We could give you an x, you plug it in and get a y, or I give you a y and you solve for the x. Now, some statisticians and mathematicians might not recommend the working backwards, but it can be done if you're, kind of cautious about it. And we'll talk more about that as we go throughout this unit. So let's look at 3 examples of models, just that way you kind of get a feel for them. So here is a table that shows the number of new stores in a coffee shop chain that opened during the years 1986 through 1994. So we have years, and you'll see a table here, 1986 all the way through 1994, and this is how many stores there were of a particular coffee shop chain. So in 1986, there were 14 new stores. In 1990, there's 110 new stores. In 1994, there's 681 new stores. So the first thing we do actually is be careful. When we're going to go ahead and plot this, x equals 0 is 1980. So this would actually be an x value of 6, an x value of 7, 8, and you get the point. So it's important to understand that, when we actually make a scatter plot of this, we don't use 1,980. I mean, you guess you kind of could, but we typically don't. We just say, okay, 0 represents 1980, and then we calculate what the values would be from 1980. All right, so what happens is, we're going to make a scatter plot of this, and we see it. And then again, your job is to figure out what models this best. And there's going to be future videos that talk about all of that and all so forth. But this video is just really focusing on understanding what a model does. So once we say, oh, that kind of looks exponential, right? Then what we got to do is find the exponential function that fits this model. And our calculator is going to do all of that for us. But right now I'm giving you the answer. But in the future, you're going to use your calculator to get this function. But right now I'm giving you the function. So this is a model, the exponential model that fits that data. So 1.055 is my A value, that's my coefficient. 1.586 would be my B value, because remember, A times B to the X is the exponential model. And then again, we can actually plot that model on the graph, and we see that it really does go through the data very nicely. Again, the model fits the data very, very well. It doesn't fit it perfectly. It doesn't go through every single dot dead on. It goes through like this dot, it goes through perfectly in this dot, but a couple dots here and here, it's really close to, but it doesn't go directly through them. But again, that's the point, is no model's perfect. So again, once you have a model, we could really ask you a lot of questions. So I could say, what about, what would we expect for 1995? In 1995, what would you expect? Well, 1995 would be an X value of 15 years after 1980. So again, we would just say, all right, well, to predict this, we're going to take 1.055 times 1.586 raised to the 15th power. And we could go to our calculator, type that in, 1.055 times 1.586 raised to the 15th. And we would predict that in 1995, there's going to be 1,066. Now there's going to be some decimals on this, so please understand that you're going to typically round that to the nearest whole number because, again, you can't have 0.11 of a restaurant. But so we could say, hey, we predict that in the year in the year 1995, we would predict that there would be about 1,066 new coffee shops opened up. So we could use it that way. And again, like I said, we could also use it backwards. So for example, I could say something like, all right, when do we think, in what time do you think there will be 2,000 new coffee shops? So we would take 2,000, we'd set it equal to 1.055 times 1.586 raised to the X, and we could solve for X. Now, I'm not going to do that right now because that's not the point of this video, but we've already learned in previous units how to solve all different types of functions, so you should know how to be able to solve that for X. But anyway, then you could work backwards and solve for the year that we would predict there to be about 2,000 new coffee shops. All right, here's another example. So this table shows the high temperature and the number of soda pop cans sold at a vending machine for 8 days. So we looked at 8 different days and we recorded the high temperature on that day and how many soda cans were sold through a vending machine. So we have the data here. The explanatory variable is the high temperature, and that's going to go on the x-axis, and the y-axis is the number of soda cans sold on the y-axis there. That's the response variable. And we don't see a beautiful pattern, but it does look fairly linear, right? I don't see any major curves going. It doesn't look logistic. It doesn't look like a quadratic, right? It looks pretty linear, so we fit a line through it. So this is A plus BX, or, I take that back, I'm sorry. AX plus B is the formula there. That's our linear formula. And then again, our coefficients for A was 16.416 and B was negative 621.826. Now, if you're wondering, where did you get those from? We're going to teach you that. Our calculator does the large majority of that work, but this video is really just focusing on knowing what a model is and what you could do with a model. So once again, we could type that function into our calculator and we see that it doesn't fit the data perfectly, but it does fit it fairly well. It goes through this dot and other dots it's pretty close to, but that's the point, right? No model's perfect. So then how could I use this model? Well, I can use it both ways. So I could say, all right, if it's going to be 90 degrees is the predicted high, plug 90 in and tell me how many soda pop cans we would predict that we're going to sell on that day. Or vice versa, we could say, hey, on a particular day, there was 600 soda pop cans sold. Can you solve this backwards for X and tell me what we think the temperature was that day? So again, that's kind of what we could do with models. We see a pattern in our scatter plot, we fit a particular function that models it pretty well, and then we could use that model. All right, let's look at one more example here, and I chose a logistic one because these are kind of cool ones. But all right, so the table below shows the population of Florida in millions at the beginning of each decade since 1900. So again, we're going to let X represent the years since 1900. So year 0 would be considered 1900 right here. This would be 10 years, 20 years, and so forth, all the way to 110 years since 1900. And the population is in millions, right? Now, if you look at this, you do kind of see that slow S, where it kind of has a slow increase in the beginning, a pretty fast increase in the middle, and then it does start to slow down. So this is logistic. But again, there's going to be later videos that kind of teach you how to know what model to use. And I will say this, just to kind of do a quick pause, right? If you're confused, like I don't know what model I'm supposed to use because this could be exponential and maybe somebody else says that could be cubic, who knows? Well, we're going to teach you later videos on how to kind of judge what model is best. And your calculator is going to do a lot of that for us. But we do kind of see a slow S here, which is our logistic model. And another reason why this makes sense is that the population of Florida isn't going to be exponential because it's not going to continue to just get bigger and bigger and bigger. And there's never going to be a point where there's 1 trillion people living in Florida, right? It makes sense that there was 1900, the population was booming and it got pretty big fast. But then now that we're into the 2000s, the population is slowly kind of steadying off. It might be increasing, but it was slow in the beginning, and then there's a big boom in the population across the entire world, and then now it's kind of slowing off. It's going to increase a little bit every year probably, right? The populations are increasing, but it's kind of leveling off. It's not making any major increases as well. So that's that kind of logistic function, logistic model. So anyway, we have our coefficients here. Again, where do you get these numbers from? Your calculator, but there's our C, there's our A, and there's our B, and that's the logistic model. So once again, I could say, all right, in 2020, 120 years from 1900, what would you predict the population of Florida to be? And all you got to do is plug 120 in for X, use your calculator, and you're going to get the predicted population in Florida. But again, we could also use these backwards. We could say, okay, what year do we kind of predict that there will be 20 million people living in Florida? So that's where we would put a 20 right here for the Y value, and then we would solve for X. Now that's definitely a tougher equation to solve for, but again, we should be slowly getting better at solving equations. In fact, I'm actually going to take the time to show this one just because it is a little bit tricky and it could pay off in the long run. So we have 20 million equals, and again, 26.6970 is on top. 26.6970 divided by 1 plus 81.9039. 80.9039, and did I type that right? It's 81.9039. Sorry about that. 81. Again, I'm trying to copy here. Should have had it ready. And then again, here comes the tough part. It's e to the negative 0.0480x. 0.0480x. All right, now how do we solve this one? Well, the first thing I would do is I would cross multiply. So I'd have 20 times 1 plus 81.9039 e to the negative 0.0480x equals 26.6970. Divide both sides by that 20, so we get 1 plus 81. A lot of writing here, to be honest, just because of all the decimals. So be very careful. Try to be as neat as you can. And I wouldn't round anything until the very end. So I'm just going to hit divide by 20 here. I'm not actually going to do that math yet because, it's going to be some ugly decimal. I don't want to round the middle of a problem. All right, next step is I'm going to subtract this 1 over. So I'm going to put a minus 1 over here. And then I'm going to divide by the 81. So I have e to the negative 0.0480x equals, again, this is very ugly, but check this out. 26.6970 divided by the 20 minus 1, and then all of that is divided by 81.9039. And then what I got to do is now that I isolated the exponential part, I got to use my log, right? So logs equal the exponents. This is where it's going to get really ugly, but it's going to be the natural log, because that's a log base e, of, okay, and again, don't get confused. This is ugly, I know that, but it is just a number. And you would just slowly type that into your calculator to get that number, but it is a number. And that would equal the exponent of negative 0.0480x. So again, I'm just using the definition of a log, natural log, which is log base e, of this ugly number equals the exponent. And I got one more step, and that is to divide by the negative 0.0480. So if I take this natural log, and again, I'm just got to use my calculator. I don't want to round in the middle of a problem. So you're going to use your calculator to get that number, natural log of that number. And then again, sorry for the messy handwriting here, but I'm going to divide all of that number by negative 0.0480 to get my final answer. And my answer is going to be a number. And that, again, X is the number of years from 1900. So that'll kind of give me an idea of when that's going to happen. So, oh boy, that was a tough solving one. But again, it's really just solving an exponential equation, which we should be, somewhat decent at. So, okay. So kind of just going back, the whole point of this video is really to make sure you understand that we have a scatter plot of two quantitative variables. And in that scatter plot, we see a pattern with the scatter. And the pattern could be all different types of functions that we've talked about. And what we want to do is find what function fits that data the best. And then we're going to use our calculator to actually give us that function. And that function is what is called a model, because it models what we see in the scatter plot. So that's a quick rundown of what modeling is and how we can make a connection between the data, the scatter plot, and the function that best represents the pattern that we see in that scatter plot. So at the end of the day, that's what modeling is. And, really the next task is going to be how to utilize your calculator to get the model for us. And we'll see that in the next video. All right, guys, thanks a lot.